This video will go through the process of inverse filtering to obtain the airflow waveform at the glottis during a vowel. And in inverse filtering, we start out either with an airflow signal as measured using a CV mask or a circumferentially vented mask, and that measures the airflow at the mouth. Or we can use a microphone to get the pressure signal at the mouth. It should be a omnidirectional electret microphone, or sometimes called a capacitance microphone, and it should be held a few centimeters from the mouth, as I'm holding it here. Now, the inverse filtering we'll be doing today will be from a microphone signal, and this is measuring the pressure waveform at the mouth, and the inverse filter will extract from that the airflow waveform at the glottis in the larynx. Now, looking at what I have here now is the waveform of a pre-recorded signal of me saying pa pa pa, pa pa pa. Let's play this. I can play this back from the Waveview screen, and I'll click on original. Pa pa pa, pa pa pa. Okay, so this is the syllable pa pa pa, pa pa pa. Now, the original signal that will be on the center screen. The top screen will show the results of filtering as we go through the different filtering stages, and now it's the same as the middle screen because we have all the filters turned off. Now, I'd like to point out that there is a problem in this recording, and now we'll get around the problem, but you should be aware that if you look at the center pa, that it's flat at the top, and this is because the signal was recorded slightly too high. The signal should look more like the third syllable or any one of the ah syllables. And so this is called clipping, and so when we inverse filter, we'll take something from the third syllable, not the second. It's only a slight amount of clipping, but it's enough to make some distortion in the waveform. Okay. Now, before inverse filtering, I will change the put in an integration step to make the waveform the flow instead of the pressure. To do that, I click on integral here. Now we have airflow. Well, actually, airflow is on both waveforms. And I'll expand the amplitude scale. And generally, you want to keep the amplitude scale large, strong, so that you see the waveform in detail. as long as you don't go off scale. The gain setting doesn't affect the operation of the filter. It just affects how much you see on the screen. So you're free to pick any amplitude scale that you want. Even if you if it goes off scale, the inverse filtering won't be affected. Okay, I have it now at a gain times 4, and the integration is on. Now now notice on the bottom we have the first three formants, first, second, and third formant, and a low-pass filter called a smoothing low-pass filter, which takes out energy above the cutoff frequency here. Now we'll take out the formants one by one. What you're seeing on the screen is mostly first formant energy. So we'll take out the first formant first. To adjust the first formant, you have to eliminate the second and third formants approximately using the smoothing low-pass filter. Now we could set that low-pass filter above the range that the first formant could be at, and I have it here set to 1200 Hertz. Now if I turn off that filter, so now that puts second and third formant energy in there, but if I turn it on, it removes the second and third and just leaves the first. So now I can adjust the first formant by the following procedure, and you can see that that now you have just one formant here, and the first formant, and we could click on the period. We could determine the period of the first formant by clicking on two succeeding peaks in the waveform. And in the information bar on the screen, it'll say that the period is 1.4 milliseconds. The reciprocal of that is the frequency of the first formant, which is 711 Hertz. And so we want to set that to 711 Hertz. Now I'll turn on the first formant. Now it's set to 490. Now the damping of the formant is set to 0.04, which is a good setting for a microphone signal. And the second and third formants are set to 0.03 and 0.02. Now those values of dampings are default values, and they're good for a microphone signal. And there's no need to change them. Now, as I can turn up the frequency of the filter by clicking on the arrow here, or I could use the cursor by the side of the first formant and move it up. Now, and you notice as I get past 711, the first formant energy goes out. There's 720, and then comes back in again. So we can zero in. Right there is a minimum value of the first formant, 737. Now I want to get it down to closer to 710, oops. And so I'll use this to go. I'll use the arrow, which enables me to to do a finer tuning. Here is 654, 660, and 676, and 700, and there's 720. Okay, 715, 710. So now the first formant is removed from here. What you're seeing on the screen is the second formant. There's a little bit left of the second formant. And the low-pass filter did not take this out entirely. So now we will then proceed to take out the second formant. Now to do that, we'll move the low-pass filter above the second formant. I'll pick 1600 hertz. Now that's taking out the third formant and the fourth, but leaving in the second formant. And what you could see here is the second formant. Now I could then turn it. Well, the second formant filter is off, and I'll try to measure the frequency of the second formant on the screen. Now I'm going to turn up the gain, and that's going off screen on the top, but it doesn't matter. Now I could see the second formant oscillations more clearly. And I try to get the same place in the cycle with two succeeding, successive oscillations, and I get a period of 0.91 milliseconds, which is equivalent to a frequency of 1100 hertz. And so I'll have to set the second formant filter to 1100 hertz. First I'll turn it on, and you can see that even 1300 hertz takes out a lot of it. But to get it down to a minimum, I could set the frequency closer to 1100 hertz. Now I have the first and second formant filters out. Now, and what's left is a third formant. And now I'll turn up the low-pass filters, because that's decreasing the amplitude of the third formant, and I'll set this up to say 2200 hertz, which is above, or 2400 hertz, which is above the third formant. Maybe 2500 hertz. That's above the third formant, and so the third formant then so that's above the second formant, and it's taking out. Wait, no, it's so it's taking out the fourth formant and leaving me with the third formant. So now I'll expand this a little more, and I'll do the same procedure, picking two succeeding oscillations, successive oscillations, and all right, I marked with the left cursor and the right cursor, and I have a period of 0.45 milliseconds, which is equivalent to a frequency of around 2200 hertz, which would be the third formant. So I have, actually, the third formant is set pretty close to 2200 hertz. So when I turn it on, the third formant disappears. And I'll turn this down to 2200. Now again, if we move the slider up and down, we can see the effect. If it's set too high, the third formant comes in, and if it's set too low, the third formant comes in. And it goes, at the minimum, occurs at about here, which is about 2200 hertz. Now, what's left, the remaining oscillations, are the fourth formant, and if we turn off the low-pass filter, we can see the fourth formant. And the fourth formant, we have no filter for the fourth formant in Waveview, so we use the smoothing low-pass filter set at 2500 hertz, which is, or maybe 2400 hertz, to take out the fourth formant. So right now, if I reduce the gain to bring it on screen, I could see the glottal pulses, the glottal airflow pulses, let me read it. Okay. And you could see that the glottal point of glottal closure is here, and zero airflow is at the center line here, but the zero airflow is not maintained with the if you're inverse filtering pressure. So a zero airflow is really this part of the waveform. And then right here, the vocal folds start to open and the airflow increases. And if we want to know the fundamental frequency, we can click at two successive glottal closure points, and we get an interval of 6.49 milliseconds, which is a fundamental frequency of 154 hertz. And that was my fundamental frequency in saying pa. Okay. If I change the time scale to get the entire syllable, you can see that this was the closure for the P, and the release was at this point, and then the aspiration comes here, and then the vocal folds are coming together at the end of the period of aspiration, and then you have the voicing. Now, there's one other step here. Let me expand this again. Now, in a microphone signal, there's low frequency phase distortion, and we can take that out or cancel most of it by this is the signal by using the low frequency phase compensator for channel A. Channel B, there was no channel B here. I only recorded airflow. Normally, we would have perhaps an electroglottograph signal on channel B, but there was no electroglottograph signal here for channel B. Actually, the compensation was on. Without the compensation, you see there's a slope to the zero flow level here, which is not in the glottal flow signal. So I'll turn the compensator on, and the compensator is set. If you want to see how it's set, we could go to Options, Advanced Options. It's set to 40 hertz, which is a good setting for a typical microphone, and a reversal filter. And the different settings available are 20 hertz, which is less filtering, 40 hertz, and a lot of filtering, 20 hertz and 40 hertz. And 40 hertz is a good setting, so I'll accept it. Okay, so there are the glottal pulses. Now we can look at the flow declination rate, which is the slope of in the closing phase, and that's of interest sometimes. And so we would, to get the rate of decrease of the airflow, we can differentiate the signal. That gives you the rate of change. Now, since we're already integrating it, if we take off the integration by clicking on neither, that's equivalent to differentiating the airflow. And that's a little off scale. I can move it. And so this shows us the rate of change of airflow. And so between here and here is the maximum rate of change. And if we go back to integration, we could see that it's a pretty much straight line between there and there. And by taking off the integration, we could get a measure of what the rate of change was in that period. Now, this was the syllable ah. Let's try that with the syllable ah. Now, if I go back and get to say 640 milliseconds, I could see. Now let's do it. Now that's pa, pa, pa. Let's go to an ah, which is here. Now I'll take some part of the steady state ah vowel and put the left and right cursors in it and expand that, and that'll show me the waveform in ah. You notice what's happened is in ah, the second formant is a little higher than in ah. So the second formant energy is not removed. First formant energy is about the same. So if we want to change the second formant, we can measure the frequency here again of the second formant, and there's a little bit of third formant in there. I could take it out by bringing down the low pass filter. There's the second formant. All right. Now, if I click first, and now the one, let's see, that's, you want to get the same part of the same part of the cycle on both oscillations, and we look at and we find a period of 70.73 milliseconds, which is equivalent to a frequency of 1378 hertz, or about 1400 hertz. So now let's go back and turn on this. Well, the second formant filter is on already. So now I'll raise the frequency to 1400 hertz. And that takes out the second formant. And so we have a waveform which is similar to the one for the ah, because the glottal airflow is not much affected by whether you have an ah vowel or an ah vowel. So this is the inverse filtering the ah vowel. Okay. And so that's the inverse filter process for a microphone signal. in two different vowels. And again, we can see this is the closure period, and then you have the explosion, and the aspiration, and then a period of steady state vowel here. Now, I used the syllable pa and pa. I put a p there, and one reason for that is that if you say p, you close your velum tightly to create a pressure, and so the velum will remain closed during the vowel in general. And so the inverse filtering, if you leave the velum open, instead of ah and ah, you would have ah, and the inverse filter process will not work as well. So I've removed the nasal, I've ensured no nasalization during the vowel by using a P consonant. And that's it. All right. We have available, incidentally, a automatic inverse filtering by listening to the vowel and clicking on this chart of F1, F2. We can do some automated inverse filtering. Now, here's the waveform for ah. And ah is this vowel here. And you can see that it's not quite accurate. So this is be roughly, and here's ah. You can see the so we get approximate inverse filtering by using this chart, and sometimes that's convenient to give you a starting place for the F1, F2, and F3 values. But as you can see, the ah is not accurate. It was 1720, and it was really supposed to be around 1400. And the ah vowel actually is not too accurate either. So this is just an approximation. Okay, thank you. We have a comparator here, filter 1. We can record the values that we've. You could read your manual to find out how you can record these values so you can bring them back up later without writing them down.